Alright, so today we're going to do 9.3, the dot product. So far we've learned how to add and subtract vectors and how to multiply vectors by a scalar. But what about multiplying vectors? Well, let's define the actual property, okay? So if we are given vector v and vector w, the dot product would look like this, v dot w. What does that mean? Yes, we are putting the vectors and multiplying together, but what actually happens is you're doing the first element of each plus the second element of each. So we're going to get down to a value, okay? So let's do that practice right now. I'm going to set this up and show you how to write it. So v dot product w would be the same as our vector 3, 4 times vector 1, negative 2. And when we put that together, what that looks like is we're going 3 times 1 plus 4 times negative 2. Okay, when we do that in our calculator, we get the value of negative 5. Alright, so that easy, right? Note that the dot product takes two vectors and produces a scalar. So like I said, you come out to a value, a number value. For that reason, the quantity v times w is often called a scalar product. So even though we're saying dot product, it can also be saying scalar product, but that tells you to do the same property here. Okay, so let's look at what properties of this dot product can happen. Well, we can do the commutative property, you know, switching it back and forth, and you get the same thing. You could do the distributive property. Okay. We can do a scalar property, so multiplying it by a value, or this one is what we're going to use a lot right now, and we want to remember that the relationship can go back and forth. When you do a vector times itself, it's the magnitude squared. Same thing, if you see the magnitude squared, you can actually do it vector by vector. Okay, so let's actually prove this identity right here. Okay, so we're mostly going to use this relation magnitude. Now what I'm going to do is I'm going to take the left side and I'm going to keep manipulating it until it looks like this right side. So what does the magnitude of v minus w squared look like? Well, if we use the relationship or the relation to magnitude, I know that this is the same thing as saying v minus w times v minus w. Okay. Now, if we do the dot product here, I would get v times v minus w plus negative w times v minus w. Okay, and actually guys, I didn't do the dot, well, I did the dot product, but I also had the distributed property in there. So I have that u times this. So this would have been our u, and we're doing this u, each u times this. Okay, so it's kind of that dot product and distributed property all together. Alright, so now what I'm going to do is do, again, that distributed property even more. So I get v times v minus v times w. Okay, let's look at this. This is plus, but really there's a negative here. So let's do a negative. And I'm going to switch this commutative property. I'm doing this all together. Okay, that's from right here, guys. And then negative w times negative w is a positive. And I'm going to put that as w times w. Okay. Alright, well, as you can see, how many of these do we have? Well, we have v times v minus, and we have 2v times w plus w times w. And what do you know? We can use now the relation to magnitude again with those two vectors that are multiplying by itself, and we end up with magnitude v squared minus 2 vw plus magnitude w squared. And we just proved it. It's the same. Okay. Alright, geometric properties. So suppose v and w are two non-zero vectors. Okay. If we draw v and w with the same initial point, if we draw v and w with the same initial point, we define the angle between v and w as the angle theta determined by the rays containing the vector. So all three of these photos have the initial point being the same. Okay, so as you can see, theta in between here, there is no theta, it's 0, because they start at the same point and they go in the same direction. Now, of course, the magnitudes are different, but they are in the same direction, so that theta is 0. Where here, we have our initial point being the same, and we have them going in different directions here, not so much opposite, because this is the opposite direction here. So as you can see, the opposite direction would be 180 or pi. And then anything in between, we would say is between 0 and pi. Okay, the reason for it is if we came back here, we would then keep it in between. We would go theta here instead. So our theta is always going to be between 0 and pi. Alright, geometric interpretation of the dot product. If v and w are non-zero vectors, then v times w is actually the magnitude of v times the magnitude of w cosine of theta, where theta is, of course, the angle in between v and w. Okay, now there is a proof in our notes, in our modules, but don't worry about that. So we're going to use this if we have theta and the magnitudes, okay, and depending on what they want us to do. So the other thing we can use from this is we actually can solve for theta. We can solve by theta by doing some algebra here. If you look, let's get cosine by itself. We would divide by those magnitudes. That's where that comes from. And then, of course, how do you get theta by yourself is you do inverse cosine of that. So those are the things we're going to do right now. We are going to find the angle in between the two vectors. Now, if we need theta, that means we also need our magnitudes. So the first thing that I want to do is find our magnitudes. So the magnitude of v, remember, is the square root of a squared plus b squared. So when I do this, and I'll write it out just for you guys to remember, but I'm probably going to do it quicker as we go along in this lesson. And that comes out to be the value of 6. When I do the same thing for w, I get the value of 2. Alright, so that gives me those two pieces there. But now I need the dot product. So I need v times w, which of course is our vector 3, negative 3 square root of 3 times negative square root of 3, 1. Just like we did earlier, you multiply your first elements and then add your second elements, multiply together. When we do that out, we get negative square root of 3, or 3 square root of 3 minus 3 square root of 3. which of course we now can combine as negative 6, square root of 3. Okay, remember it's asking yourselves how many square roots of 3 there are. There are negative 3 here, negative 3 here, so negative 6 altogether. Okay, now we have all our parts, so we can actually put this into our formula. So I'm not going to write cosine theta, guys, because we're still going to take the arc cosine. So I'm just going to write straight out that theta equals our arc cosine or inverse cosine. And then I'm going to put our values in there. So negative 6 square root of 3 all over 6 times 2. Now when I do that out, I get arc cosine, and now we get negative square root of 3 over 2. Now look at your unit circle or in your head, and remember that even though there are two values of cosine on our unit circle that are negative 3 over 2, we are looking for the one that is between 0 and pi, which means that theta equals 5 pi over 6. Very good. Now let's do this one. So same idea, guys. I'm going to go through this a little faster. So the magnitude of V, check that out right now. If you have to pause the video and then see if you have that, that's fine. Well, the magnitude of V is actually 0, right? So, oh wait. Sorry guys, it's not. I actually did something. What is that for? It's 2, right? No, it's not. But guess what? This is why I'm confusing myself, because when I did this ahead of time, I actually, I'm going to show you right now, is I did the dot product first. And if you look, the dot product, right, 2 times 5, negative 5, that gets us 2 times 5 plus 2 times negative 5, which equals 0. Okay, and this is why I did the dot product first, and this is why I confused myself. Because if we look at theta right here, and we started putting in our stuff, so arc, cosine, we would get 0 over those magnitudes. The idea, guys, is it doesn't matter what these magnitudes actually are, because 0 over any number is 0. So that's why I confused myself in my notes. Now, of course, if you did that out, we would find that number, right? This would be, so 4 and 4 is 8. So this would be the square root of 8. And this would be the square root of 50. But again, it doesn't matter because 0 over any number is 0. And then we're looking at cosine between 0 and pi, that it equals 0. Well, that is at pi over 2. Okay. So if you did do the magnitudes, it's okay. It's an extra step, but you don't really need it just for the fact that we know it's 0. Okay, now we have one more here we're doing. So there must be something different with this one between the other two, because why would I have you doing the same thing over and over and over? Okay, so again, just because I ran into that situation before, I'm actually going to do the dot product first. Okay, so we get 3 negative 4 times 2, 1. Do that out, we get 3 times 2 plus negative 4 times 1, which equals 2. Okay, so we do need the magnitude, so magnitude of V, we do that out, we actually get the value of 5. Magnitude of W, we get the square root of 5. Okay, again, if you wanted to pause it right now, calculate that out, make sure that's what you got. So when I put it into theta, theta equals arc cosine of 2 over 5 square root of 5. If we look at this, and I'm actually going to rearrange this to see if it helps me out, that square root is in the denominator, and sometimes we don't want that. So it ends up being 2 square root of 5 all over 25. But as you can see, this is not one of our easy values on our unit circle. So instead, we are just going to keep this as our answer because it would be a decimal. Okay, so only break it down all the way down if it's on your unit circle. If not, you can keep it in this form. Okay, orthogonal vectors. So geometrically, when orthogonal vectors are sketched with the same initial point, the lines containing the vectors are perpendicular. Two vectors are orthogonal if and only if their dot product equals 0. Okay, so here's our orthogonal projection. Okay, we have vector v, vector w. What we're going to do is project another vector here that makes a right angle onto w, and that means this vector p, this magnitude, right? This is our orthogonal. It creates that 90-degree angle. Okay, so we're finding the orthogonal in that case. We call p the orthogonal projection of v onto w. So we're going from v to w and making that right angle. If we were going to w onto v, we would be going right here. Okay. Alright, so what does that do? Well, if v and w are non-zero vectors, the orthogonal projection of v onto w is denoted by this. So the projection. Okay, we are actually finding the position. Okay, and we're going to draw it out. So we have here in example 4 that we have a vector 1, 8 and negative 1, 2. We're going to find the projection. Okay, we're going to find that orthogonal projection and then plot it. Okay, so again, that orthogonal projection is making that perpendicular angle. So here's what we need, right? I can put in v, I can put in w, and then I'm going to find the magnitude. I'm actually going to write this in one whole thing and then do calculations by itself, guys. So the projection, w, so v onto w. If we were doing w onto v, we would have v here, w there. Alright, and then we have, I'm just going to put these vectors in. So 1, 8 dot product with negative 1, 2 all over the magnitude of w. So make sure you're writing in the correct vector squared times the vector w. Alright, so let's do some calculations out here. Oops, and this is equals. Alright, so our dot product comes out to be negative 1 plus 16 all over, and then our magnitude is the square root of 5, and we know we have to square that, and then we're going to multiply it. So this comes out to be a number, and we're going to multiply it by the vector negative 1, 2. Okay, so we end up getting another vector. So we have 3, negative 1, 2, which of course, oops, scalar multiplication, we get the vector negative 3, 6. Okay, so I'm going to try to draw this nicely so you guys can see what's going on here. Now, I don't have a ruler, and my scale is going to be a little bit off. Alright, let me get some colors out here. So I'm going to first do V. So 1, 2, 3, 4, 5, 6, 7, 8. Now, all of these start at 0, 0. We're going to start with the initial being 0, 0. Okay. And of course, without a ruler, it's not going to be the straightest of lines, guys. Okay, sorry for that. So we get V. Now we're going to get W. W is negative 1, 2. Negative 1, 2. Now, what I'm going to do actually, and this is the other way I'm doing this, I'm actually going to plot negative 3, 6, and we'll see if it creates that 90-degree angle. So there's negative 1, negative 2, negative 3, 1, 2, 3, 4, 5, 6. Okay? So, if I were to continue W and connect it to V, does that create a 90-degree angle? Well, of course, my drawing is no, but yes, it does. It will make a 90-degree angle. So we have to extend. In this case up here, we had to actually pull back on W to get that 90-degree angle. But on this one, we're actually extending the vector of W to make that 90-degree angle. Now imagine, guys, they do all of this when they're doing physics and, let's see, aircraft stuff and space stuff. It's crazy. You have to predict the projection on where you're going to land and all that other stuff. It's great. And actually right now we're going to do some physics. So let's see how this works. Okay, so work. We close this section with application of the dot product. In physics, if a constant force F moves an object a distance d, then the work W done by the force given by the magnitude of the force times the amount of displacement. Ooh, that was a lot. Really what that means is work equals magnitude of the force times the distance. Okay? So if the force is not applied is not in the direction of the motion, then we can use the dot product to find the work done. Okay, so we need to be careful of which direction it's going in. So here we go. I want to make sure I give you enough space in here. Work as dot product. So suppose a constant force F is applied to move an object along the vector PQ from P to Q. The work done by F is given by, so we actually have two equations here. We could say that work is the force times that vector, or the magnitude of the force times the magnitude of the vector times cosine of the angle. So it all depends on if you have theta or not. Okay. Example 5. Taylor exerts a force of 10 pounds to pull her wagon a distance of 50 feet over level ground. Find if the handle of the wagon makes a 30-degree angle with the horizontal, how much work did Taylor do to pull the wagon? Assume Taylor exerts the force of 10 pounds at a 30-degree angle for the duration of 50 feet. Okay, I'm going to show you two ways. I'm going to do the two equations. So first, like any word problem, the best thing to do is draw it out. So we have our little wagon. Doop, doop. Okay, and we're going to pull it 50 feet, right? We're going 50 feet. Now, I don't know if you guys know, but most wagons, their handle is pivoted from the point. So we have our handle here. And the angle from the horizontal with the handle of the wagon is 30 degrees. And of course, you're pulling with the 10 pound. Okay? Alright, let me get this focused so you guys can see what I'm going to do next. That didn't do it. There we go. Okay, so the first thing I'm going to do is I'm going to do the way one, which is the first equation, which is work force times the vector PQ. Okay, so what we are given is that the magnitude equals 10, because that is our force of what we're doing, okay, and we are given that the theta is 30. Okay. Alright. So if we wanted to use vectors, you need to remember that to find vector f, it's our magnitude times cosine of our theta sine of our theta. And luckily here we can use our unit circle. Don't forget though, guys, we are in degrees and not radians. So that means that we get 10 times square root of 3 over 2, which is 5 square root of 3. Okay, sorry, I'm doing my math all together, guys. So again, cosine of 30 is square root of 3 over 2. Square root of 3 over 2 times 10 is 5 square root of 3. Sine 30 is 1/2. 1/2 times 10 is 5. So there is our vector f. Okay? And then we are pulled along the x-axis, guys, right? So actually, if we think of vector PQ, we are starting at 0 and going 50. So what is that point? That would be the vector 50, 0. Because we're just going horizontal and we're going towards the right there. Alright, so as you can see now that we have vector f and vector PQ, we can just do the dot product. So work equals, and we're going to go this vector 5 square root of 3, 5, times vector 50, 0. Of course, I realize that I'm writing and you guys can't see it. There we go. So when we do this dot product out, we end up getting 250 square root of 3. So it is possible to have the magnitude and theta, but use vectors. We just have to convert them into the vectors first. Now, way 2, I'm going to use that work is the magnitude of the force times the magnitude of PQ cosine theta. Alright, well, we have a bunch of this already, right? We have 10. And then, of course, if we find the magnitude of our vector, we would get 50 squared plus 0 squared. And then we would take the square root of that, and what do you know? It is 50. And then we have cosine of 30 degrees. Now, we get 10 times 50 is 500. And cosine of 30, I don't know why that looks like theta, is square root of 3 over 2. So 500 times the square root of 3 over 2 is 250 square root of 3. So we do get the same answer. You want to know both ways because, one, you don't know what they're giving you. They gave us our force and our angle, which allowed us, and our distance, which allowed us to do this right away. But if part of the question is asking for the vector, then you're going to have to do it this way. So it's good to know both. And we're done.